All right, for the first homework problem on homework light number 2, so the second light homework, it's a reflection problem, and what makes it challenging is that there's a number of angles involved and a number of triangles to look at. But there is a clear path to get to the answer. So it starts with giving you what this angle is, alpha. So in my example, alpha was 70, and it's asking you to find this angle, beta. And I put in labels for these A's and B's just to keep things straight. So the first thing I did was looked at this triangle, and so I said, well, this angle I'll call A and this angle I'll call B. And then because of the law of reflection, B is the same here and here, and A is the same here and here by the law of reflection, because the angle that it comes in is the same as the angle it goes out, and same thing over here. So I know those two are A and those two are B. Okay, so let's look at this triangle. Well, the angles of a triangle have to sum to 180 degrees. So if this is 70, then A plus B has to be 110. So now I know what A and B are together. A plus B has to be 110. All right, but I need to get to B. So somehow I need to deal with this triangle. And the next thing to do is to look at this and this and this together. So all three of these angles, this one, this one, this one, have to add to 180. So that means this angle in here is 180 minus 2a. Likewise, this angle is 180 minus 2b. Okay, so this plus beta has to be also 180. And so then we can write this equation down. Beta is 180 minus these two angles. And so if you add these together, 180 plus 180 is 360. And then we have minus a 2a and minus a 2b. Minus a 2a and minus a 2b. Do a little bit of rearranging the equation. You can factor out the 2, and you get this is equal to 2 times a plus b. And you notice that the minus sign went away because that's a minus, and then a minus makes these both positive. But then you have a 180 minus a 360, so you get a minus 180. Now, this is nice because we know what a plus b is. A plus b is 110, so we can plug in 110. 2 times 110 minus 180 ultimately gives you 40, which is the answer to this problem, at least for my numbers. Okay, so I got one question about the first homework problem and another question about number 9. And this is the one on myopia. These problems are always confusing to me, the myopia, hyperopia. I have to think through it every time I get to them, no matter how many times I've done them. I always have to think through these problems like from scratch again. So let's do that. I brought in the pictures here for myopia. Myopia is corrected with a diverging lens because the lens is too strong. So it spreads out the light because the lens over focuses. All right. Now what happens when the light over focuses is that you have a far point. So when you're nearsighted, you have a far point. You have a point out in the distance that is as far as that you can see. Okay. Beyond that, you can't focus the light. So what you need to do with myopia is take the distant object and bring it closer. Now, to extend your distance out forever, you can extend it out to, let's say, infinity. Then you're taking an object that's infinitely far away and you're bringing it to the location of your far point. The bottom line is the image distance has to be, or the image location, I should say, the image location has to be at the far point. Okay, now there's usually other factors to consider in these problems, like the lens is not directly on the other lens, on the lens of your eye. it's set out, in at least in my example, it was set out 2 centimeters from from the lens of the eye. So that's why I was careful to say the location of the image has to be at the location of the far point, because the image distance is not necessarily the far point distance, because the far point distance is 23 and the lens is sitting out 2. That makes this distance here 21. Okay. Now, to make things even more complicated, when you're dealing with diverging lenses and the image is on the same side as the object, the image distance is technically negative. So that's why I wrote the equation this way here. So minus di, so I'm accounting for the fact that the image distance is negative, minus di plus 2 gets me to the far point, 23. So solving for this, the image distance is negative 21. Or another way of saying it's 21 centimeters in front of the lens. All right. And so from there, we can use the lens equation to figure out the focal length and the power of the lens. When it's myopia, the object that you're trying to focus is infinitely far away. So we put that in as infinity. 1 over infinity is 0. So really the focal length is the same as the image distance. Okay, because the object is infinitely far away and this part is 0, the focal length is just equal to the image distance. So in my case here, the focal length is negative 21. For diverging lenses, focal lengths are always negative. But then to calculate the power in common units, which are called diopters, you need to convert the image distance, object distance, focal length, all of those things need to be converted to meters in order to get the power to come out correctly. So when you do that, 1 over minus 0.21 is minus 4.76 diopters. And that's the power of this lens that would cause the light from infinitely far away to create an image here. And when you look at that image with your eye, the light from the image gets focused onto the retina. So these are very complicated problems. There's a lot of geometry to them. But ultimately, you find the image distance, and the image has to be at the far point. And the object is at infinity. Plug into the thin lens equation, and you can find the power, you can find the focal length.